First of all, a legal disclaimer. I'm here as a freelancer today. This has nothing to do with my day job, and the people paying me are happy that I do not mention them. And now I will give you a presentation on Jordan algebras and beyond. Okay, so I will start with the summary. First of all, I will talk about the early Jordan. With this, I mean the first papers Jordan wrote on quantum theory and the very early ideas he had to generalize quantum theory right from the start. Then I will go to the guest of honor, the Jordan algebras and octonions, which was the research topic Jordan pursued from 1932 until 1949. Then I will talk a little bit about near rings and quasi rings. This was another topic Jordan pursued directly, delinearized quantum theory by working with nonlinear observables. Then I will briefly discuss skew lattices, another brainchild of Jordan, a generalization of lattices with non-commutative join and meet operations. Finally, in the Jordan block, I will discuss his final work on generalizing quantum theory, going beyond simple non-associative algebra to really non-associative algebras, so even non-power associative algebras, and possible links to modern ideas. Then I will, in the end, briefly talk about Gunther Ludwig's work. Gunther Ludwig was a theoretical physicist who wrote his habilitation thesis on Jordan's theory of gravity, but later also turned into the foundations of quantum theory. And for example, he was one of the pioneers of generalized probabilistic theories. And of course, I will also end the talk with an outlook. Okay. So then let's have a start. Actually, this should have been with an animation, but it didn't work. Anyway, okay. So Jordan started his work, or also his career in science, in 101 year ago with a paper on the radiation theory of light. At that time, there was a huge discussion between Bohr, Kramers and Slater, and Einstein and others on the nature of light, whether light needs to have a particular interpretation or could still be a pure wave-like phenomenon. And there was the BKS theory, which postulated that light has no particle aspect, it's purely wave-like, but this would have led to a violation of energy conservation and momentum conservation. And in his first paper in physics, Jordan compared Einstein's and the BKS theory and compared them at the time. And at that time, he was willing to accept that even energy and momentum conservation may not be fundamental and may be violated, just as a reminder how radical physics and the theoretical physics community was at the beginning of the 20th century. As it later turned out, Einstein was right, and energy conservation is maintained, and we have a particular aspect to light, photons. And then Jordan and Heisenberg and Born were the pioneers of what's now called matrix mechanics, which was the idea to describe physical quantities like momentum, energy, and position by Hermitian matrices. And interestingly, we celebrate the 100th anniversary of this discovery, and it was Heisenberg who noticed that one can describe physical quantities like transition frequencies by non-commutative variables, but he did not know much about matrices or other non-commutative mathematical structures. Then he talked to Born, and Born then mentioned this on a train travel, and Born mentioned maybe we have to use matrices. And next to him was sitting a young Jordan who said, I'm familiar with matrices because at that time, Jordan was an assistant to the mathematician Courant in Göttingen. And so Jordan became involved into matrix mechanics. One interesting aspect about matrix mechanics, and the first paper on quantum mechanics, it was also called on quantum mechanics by Born and Jordan, was that in a footnote in the chapter on quantization of the electromagnetic field, Jordan mentioned that maybe we have also to use matrices to describe the space-time coordinates of the electromagnetic field strength tensor. Because until today, we still use a classical space-time description in quantum field theory. So the field operators are operators, but the space-time coordinates are still classical numbers. And already in 1925, in a footnote, Jordan proposed to go beyond this and do something which we would now call space-time quantization or non-commutative geometry. Even more radical, in 1927, Jordan proposed to go beyond Hermitian matrices or self-adjoint operators to describe physical quantities. This was related to a hangover from classical mechanics, so Jordan was working with canonical transformations, so mapping one observable to another observable. And he noticed that this does not work if you only work with unitary matrices. For example, you cannot turn a position variable into an angle variable or something like this. But if you need to use canonical transformations, so similarity transformations, but a simple similarity transformation maps the Hermitian operator to a Hermitian operator only if it's a unitary operator, or it's a unitary transformation. And this was the reason why Jordan at that time also looked at non-self-adjoint operators as possible observables. In this case, he looked at operators which have a real spectrum but are not self-adjoint, and so they're also not normal. And if you look deeper into this paper, it's a kind of early step into direction what we would now call PT-symmetric quantum theory or bi-orthogonal quantum theory or pseudo-Hermitian quantum theory. And this was something Jordan already pursued early on in his career. In 1928, von Neumann set up the standard Hilbert space formalism of quantum theory with self-adjoint operators as observables and unitary transformations as symmetry and dynamical transformations. And Jordan stopped his work on non-Hermitian quantum systems for quite some time after this. And finally, in 1930, in one of the very first textbooks on quantum mechanics, together with Born, both authors proposed that time, which we still treat as a parameter, as a real classical number, should also be a non-commuting operator, which does not commute with the position and momentum operators. So this was just the early radicalness of Jordan in his early days, which has still some relevance also to today's research. But science moved on, and in the 1930s, and now my animations work, that's wonderful, we had some trouble with nuclear physics. First of all, beta decay seemed to violate spin conservation, energy, and momentum conservation. There's also a paper by Heisenberg in 1932. Then there was much trouble with getting a relativistic extension of quantum field theory. First, the Dirac equation did not predict antiparticles. It predicted negative energy solutions. This was widely considered to be a problem. Finally, this is something which to some extent is even relevant today. Quantum field theories, relativistic quantum field theories predict infinity, so infinite momentum, infinite energies. This was also considered at that time to be a fatal flaw for the whole idea to mix relativity with quantum theory. And at that time, people were thinking that within the nucleus, we have electrons. For example, they considered the neutron to be a composite of the electron and the proton, and they considered it to be electrons sitting right inside the nucleus. But this would have violated the spin statistics theorem and also the Heisenberg uncertainty principle. If you just use the dimension of a typical atom nucleus and then the mass we have of the electron and then calculate the momentum uncertainty of the electrons, if they would satisfy Heisenberg's uncertainty principle, would be so high that it would fly out of the nucleus and we wouldn't have any stable kind of matter. And once again, there was this very important paper by Landau and Perls from 1931, where they tried to show that the whole concept of field theory does not make sense if you merge quantum theory with relativistic theory. They proposed that you cannot measure a single field observable, not only pairs or groups of observables. A single observable would become unmeasurable, and the whole concept of a field strength or a field as such would no longer apply if you merge a relativistic theory with quantum theory. So for Jordan, this was a huge opportunity. Instead of just dismissing all these problems, or as he at that time wrote in one of his papers, of course, you can always try to find ad hoc solutions and invent ad hoc particles. But this was a kind of criticism of Pauli's ideas to introduce the neutrino. We can also enlarge our theories and accept that it has its limits. And why did Jordan dive into algebraic considerations? He had a success experience from his earlier work in quantum theory. He had a paper with Klein in 1928 on a non-relativistic field theory, where they could show that the non-commutativity of the field operators prevents the infinite self-energy of the electron in the non-relativistic setting. Because of the non-commutativity, you don't integrate over the interactions of an electron with itself, but only over the pairs of an electron interacting with another electron. And by this, you avoid the infinite self-energy, which is still to some extent the problem today. But later, Heisenberg and Pauli showed that this does not work if you include relativistic dynamics and if you include the Lorentz symmetry. And for Jordan, this meant, okay, maybe the formalism we have does not work if you try to merge it with special relativity, but maybe an extension of this formalism works. And we know that the shift from classical mechanics to quantum theory was by going from commutative to non-commutative algebras. So why not try non-associative algebras? And this is how Jordan algebras came about. So Jordan tried to work in a systematic manner. He looked at the mathematical structure of the existing theory to find the next generalization which comes closest to the old theories. He didn't want to go so far as Landau and Peirce. He wanted to keep the measurement possibilities of a single observable. And therefore, he looked at the structure of observables in quantum theory and which properties they do have to make sure that we can measure observables, that we get eigenvalues or a spectrum or something like this. And by this way, he noticed that the ordinary matrix or operator product does not lead to an algebra for Hermitian matrices or self-adjoint operators. They do not close under this product. So the product of a Hermitian matrix is another Hermitian matrix is a Hermitian matrix only if both matrices commute, which is trivial for quantum theories. And if they do not commute, you don't get a Hermitian matrix. But you do get a Hermitian matrix always if you use the Jordan product. If you use the one half of the anti-commutator, then the product of two Hermitian matrices is a Hermitian matrix, and you have an algebra, a Jordan algebra, and to be more precise, a Euclidean Jordan algebra. That means that the sum of squares is only equal to 0 if every element which is squared in the sum is also 0. Let's say you have a squared plus b squared is 0 only if a equals b equals 0. This is the definition of a Euclidean Jordan algebra. If this holds for the multiplication of a Jordan algebra, then you have a Euclidean Jordan algebra. And Hermitian matrices closed under the Jordan product do form a Euclidean Jordan algebra. Jordan then found an important identity, the Jordan identity for the associator, which needs to be satisfied in every Jordan algebra. He was working right from the start very general. Today, we also associate Jordan algebras with commutative algebras, but Jordan started with what we now call non-commutative Jordan algebras, and the non-commutative Jordan algebra needs to satisfy the Jordan identity and the flexibility law. And his hope was that there will be a lot of non-commutative Jordan algebras with a certain subset, which is closed under the commutative Jordan product, which then form a generalized algebras of observables. This was his initial hope. He hoped that Jordan algebras will go beyond quantum theory. And the non-commutative Jordan algebra is the algebra which satisfies flexibility and the Jordan identity. The good thing is that we do have some non-commutative Jordan algebras. For example, the Octonians are non-commutative Jordan algebras, the Sedanians are a non-commutative Jordan algebra, the Maltsev algebras are non-commutative Jordan algebras, Lie algebras are non-commutative Jordan algebras. But in most cases, all of these non-commutative Jordan algebras, with the exception of the Sedanians and the Octonians, are so-called quasi-associative algebras. They originate from deforming the product in an original associative algebra. And this was a huge disappointment for Jordan. He hoped that there would be a rich class of intrinsic algebra, a non-associative Jordan, non-commutative Jordan algebra. And the death blow came later in 1934 when he teamed up with von Neumann and Wigner, and they wrote a famous paper on the classification of all Euclidean finite dimensional Euclidean Jordan algebras over the real numbers. And it turned out there are not many. Well, there are many, but they are all, with one notable exception, they are all derived from Hermitian matrix algebras over the reals, the complex numbers, or the quaternions, and there's always an associative product in the background, and they're not intrinsically associative, and they just lead back to complex real or quaternionic quantum theory. The one exception is the very famous exceptional Jordan or Albert algebra of 3 times 3 Hermitian matrices over the octonions, which is nice to have, and this has many beautiful mathematical properties and many connections in mathematics, but it was just too small and too narrow to act as a generalization of quantum theory. This was also the reason why Jordan stopped working on Jordan algebras in 1934, with one exception. He had to look at the exceptional Jordan algebra and how to do quantum mechanics with the exceptional Jordan algebra. And one of the most important things in quantum mechanics is how to calculate probabilities. So from 1949 until 1952, Jordan worked together with the German mathematician Hermann Haase, who was his boss during World War II, on how to generalize the Born rule from standard quantum theory to the exceptional Jordan algebra, and he also published 2 papers on this. What he could show is that the situation is quite different from standard quantum theory, where we use quadratic forms to define probabilities. Here we have a quadrilinear form or a homogeneous function of degree 4, so not homogeneous of degree 3, which is only semi-definite. So this means this was the form he found. What you can see here is that you multiply with 1/2, then you sum over 3 octonion valued vectors. So these are the x, y's here. And the star means that it's a conjugate element. So you multiply octonion vectors in this way as it's described here, and then you get this quadrilinear form and not a quadratic form, which is quite interesting because already in 1952, people were, in this case, Jordan was questioning the use of quadratic forms, which you normally use in quantum theory, and he had a probability function which is quite non-linear. And he also wrote in one of his papers that this that his probability function is not linear in the vectors he used. These octonion vectors, in a sense, generalize the state vector from quantum theory. And what is important, what you could also show is that these vectors, the elements of these vectors need to lie in one of the quaternionic triples or in the quaternion subalgebra of the octonion algebra. If you use octonion elements from the octonion algebra which do not associate and put them into these vectors, this form is no longer a probability distribution because you get negative values. This was quite interesting as a starting point. It might hint that if you work with non-associative algebras, you also get some kind of nonlinearity. But with this, Jordan stopped working on the exceptional Jordan algebra because he said, we have only 3 eigenvalues. It's too small. I can no longer work with it. This wasn't a nice first starting point. And then he started to pursue nonlinear observables. Already in a paper from 1934, a follow-up paper to the paper he wrote with von Neumann and Wigner, he noticed that one can also not deduce the bilinearity of the multiplication of observables from the axioms he used at that time. And that's why he, from 1950 to 1952, turned to near rings and quasi rings. I will just briefly describe what the near ring is. The near ring is a non-binary set with 2 operations. One is called addition, the other one is called multiplication. These elements do not form a necessarily commutative group under addition, so this means that addition and nearing does not need to be commutative. Under multiplication, they form in general a non-commutative semi-group, and both operations are only linked by one of the 2 distributive laws, either the right distributive or the left distributive law, but not both. And one simple example of a nearing everybody knows is the set of nonlinear operators. They form a nearing, and this is the classical example. So if rings describe linear series and fields describe linear series, near fields and near rings describe the nonlinear situation. And as an additional generalization, a quasi-ring is a near ring when the multiplication is also non-associative. This will become important later. And this was something Jordan pursued in the late 1940s and early 1950s. Okay. Another interesting aspect which came earlier are the so-called Karlsruher topological near fields. Karlsruher was a mathematician working in Hamburg at that time for his PhD thesis, and he had Hans Sassenhaus, the pioneer in group theory and also near field and near ring theory, gave him the task to classify all near fields. Near field is the generalization of a field. So in this case, the elements form a group under multiplication and not only a semi-group. And addition is necessarily commutative in the near field. And Karlsruher had the task to classify all near fields over the real numbers with continuous addition and continuous multiplication. And he found 3 well-known examples, the 2 fields of real and complex numbers. So they are near fields in the triple sense because every field is and every skew field is also a near field. Then he found that the skew field of quaternions is also a near field over the real numbers, but a trivial one. But, and this is really interesting, he found that a family of proper near fields, so with one-sided distributive multiplication, does exist if you apply the Dixon process. The Dixon process is a process found by the American mathematician Dixon in 1905, which turns a field or a skew field into a near field. You use an automorphism of the field to twist the multiplication of the field, and then you get a one-sided distributive multiplication. And Karcher found the following wonderful and very long multiplication, which can be simplified if you look here. So basically, you use the norm of a quaternion, then raise it to the power of the imaginary unit times the real parameter, and then you use this to as a new multiplication for the quaternions. And then you get a near field. What is important is that these near fields do depend on the real parameter. So if you use a different real parameter, you get a different near field. Karcher could show that near fields with a different real W have different centers, so elements which commute with all of the other elements, so they are not isomorphic. And because you have a real parameter, a real continuous parameter, you have basically an infinite set of different near fields by this process. The interesting thing about the Karcher near field is that they are topological near algebra, and they are even a topological near division algebra. So they are the nonlinear generalization of division algebras. And they have some interesting properties. The automorphism group, which was of the Karcher near field, is the group U1. The commutator group of the Karcher near field is the group SU2. And the same process Karcher applied to the quaternions can also be applied to the octonions. This is something which Jordan did in 1950. Then you get a quasi field, and this quasi field has the automorphism group SU3. And of course, then you have, let's say, for nonlinear systems, the Karcher near fields have the same status as the octonions have for non-associative algebras. They are a prime example with many nice and fascinating properties. And in the 1970s, a German mathematician named Johannes André proposed to generalize the concept of a vector space to a near vector space, and he proposed to use the Karcher near field as the starting point for a generalization of Hilbert space, and to look for a generalized quantum theory, something which was not pursued until today. That's why I'm talking about this here. Okay. In another twist, Jordan also looked at polynomial near rings. He looked at the non-abelian group, and he used the inner automorphisms of the non-abelian group to define polynomials, and then he used the composition of these polynomials as multiplication and the group operation as an addition to get a near ring, polynomial near ring, and then distributively generated near ring with non-commutative addition. His hope was that if you use group mappings on of a group, you automatically get the symmetries of like the Lorentz group symmetries for your generalization of quantum theory. And of course, today we have something like group field theory where we also work with non-commutative addition. But this was also a kind of research which was not pursued very long. Okay. Then I will just briefly mention that the famous physical chemist Ilya Prigogine also worked on non-distributive systems when he was looking in non-integrable systems, and he looked for a stochastic and nonlinear generalization of the Schrödinger equation. He worked in Liouville space and worked with superoperators, so operators acting on other operators, and he had a non-distributive superoperator, and this is in a sense a link to Jordan's theory. Prigogine had the idea to have intrinsic irreversibility at the fundamental level, and he wanted to get rid of the infinities and other trouble quantum field theory had, and that's the reason why he pursued this direction of research. There's an interesting link to similarity to the Karcher near field. In the Karcher near field, multiplication with a real scalar does not distribute with a process of forming a power. So let's say 2 times a squared is not the same as 4 times a squared. And maybe here's also a link to André's and Jordan's ideas from the 50s and the 70s. And what is important in this case is that Prigogine had an uncertainty for single observable, not only pairs of observables, but there was a minimum uncertainty for a single observable. This is something which Jordan also pursued later. Well, not later, but earlier in his later works after the 1950s. Okay, then I will go to the skew lattices. This is interesting because this was one of the long, yeah?
Sorry, it is almost now, so it is 25 minutes, so just 1 or 2 minutes, yes, you are left.
Yes. Okay, how many minutes are left? 5.
Well,
2, 3, say.
Oh, okay, then I will just finish the part on the skew lattices and then stop. Is this okay?
Yeah.
This should then work out. Okay, so this was the longest research program, but I will promise that this will become short. Skew lattices are just a generalization of lattices where the meet and join operations are not commutative. And this was based on the work from Neumann and Berkhoff in 1937, where they showed that there's a link between certain lattices and projective geometries, which are linked to finite dimensional Hermitian matrix algebras. And Jordan hoped that he could get a generalization of quantum theory by by generalizing lattice theory. And he was inspired by his work on the exceptional Jordan algebra because the exceptional Jordan algebra does form also a lattice and a projective geometry, where a certain theorem from projective geometry does not hold, the Gaussian axiom. And Jordan hoped that with skew lattices he could find more projective geometries in higher dimensions where this theorem also does not follow, because in standard projective geometry, this theorem is only a theorem in plane geometry. It does follow from the other axioms in higher dimensions. And Jordan hoped that he could find something like this if you work with skew lattices. And then the interesting thing is that the American physicist David Finkelstein also worked with non-commutative logic, which then also gives rise to skew lattices in his idea to get a space-time code and a quantum space-time theory. And finally, then we are back to Jordan's original work from the 1920s. Jordan could show that his skew lattices can be represented by real triangular matrices, so non-normal operators with a real spectrum, and this closes the circle to his earlier work from 1927, and with this I stop.
Okay, cool.